Welcome to a new video about inverse z-transform. This is our example number 3. In this example we will discuss another example step by step in our calculations and also verify this in MATLAB command window. Okay, let's look at our example. We would like to determine the inverse z-transform of this function, which is a second order system or second order expression, 8 over z times z minus 0.4. So how to determine now the inverse z-transform? So let's see that in our solutions. The calculations first. We divide, as we did in the previous examples, the function here by z. So we have this one. That means we have now 8 over z squared times z minus 0.4. And now we will use partial fraction expansion. In this case, we will have z squared times z minus 0.4. But we will still need 3 fractions. So that means we need to divide this in 3 fractions, which is then a over z plus b over z squared and plus c over z minus 0.4. So we need to determine these 3 unknowns a, b, and c. Okay, now we need to put these 3 fractions in one fraction. In order to do that, we need to make the denominators equal to each other. So that means we need to multiply the a by z times z minus 0.4 and b by the z minus 0.4 and the c by z squared, and that is actually all shown here. Now we can add them up because they have the same denominator, and also the left side has the same denominator, so we can say 8 is equal to the summation of the numerators on the right side, and that's actually shown here in the final form. Okay, now we need to determine, as said, the a, the b, and the c. So we need to select here a convenient value for z in order to eliminate all of the unknowns except one. Now in this case, if I select z is equal to 0, I will lose the a and also the z, and I will only have the b. That's actually shown here. So 8 is equal to 8 times 0 times, in parentheses, 0 minus 0.4. So this will go. This is just in detail given. B in a similar form, but that doesn't go, so it will be then minus 0.4 times b, and c is also gone because it will be multiplied by 0 effectively. So you will have 8 is equal to minus 0.4 times b, so the b will be then 8 over minus 0.4, so our b will be minus 20. So in this case we will calculate b first. Now we select for z is equal to 0.4, that means the a will go and also the b will go, so we can calculate c. That's all shown here. Now we will lose, as said, the a and the b. Then we have 8 is equal to 0.16c because of the 0.4 squared, and the c will be then equal to 50. Okay, now since we already have chosen for z is equal to 0 and z is equal to 0.4, we can of course look at this expression and try to find another value for z in order to eliminate the other parameters, other unknowns, except the one we need to calculate, which is in this case a. But there is nothing we can do about this because if we choose, for example, z is equal to 0.4, we will lose the a. If we choose z equal to 0, we will also lose a. But there is no other option. So in this case, we just pick arbitrary value for z, which is simple, just 1. Since we know the b and the c are in the previous 2 calculations, we actually can calculate the a. So we can do that. Just pick some convenient value for z and also use the values we just determined for b and c. And that's all shown here. Now we can see that we have now the b inserted here, the c, and also we have for z selected 1. Now we can calculate this because this will be then 8 is equal to a times 0.6, so that will be then 0.6a minus 12 in total here, and then plus 50. Now that will be then in total here 38. That will go to the left side, will be then minus 30. That means it will be then minus 30 over 0.6, and a will be then calculated as minus 50. So we have now our 3 unknowns. Then we can write our function, which is then f z over z is equal to this one. Now we can multiply the right hand side also by z, such that we have the f set as we had before. So f of z is equal to minus 50 plus minus 20 over z, not z squared, and then 50 z over z minus 0.4. Now we need to look at the table in order to go from this to the inverse z transform. Now the table is shown here. We have here now 3 entries. The final one here, the third entry, is used for inverse z transform for this one. This entry, the second one, is useful for this term, and the first term here is a constant, so the m is here a constant, and the n here is the exponent for this fraction, so it is in this case e to the power minus 1. So we can say the time function at the sampling instance can be also written like so. So we have here the minus 50 times the Dirac delta function kt, that's this one. Since the m is here minus 50, that's for the a, and we have this one, so we go here and we use this entry to go from this to the sampled time function. The next one is the minus 20 over z, or minus 20z to the power minus 1, which is this actually, and that means we need to put it in this way. Since n is 1, that means kt minus t, that's actually shown here. And then plus 50 times 0.4 to the power k, because the a is here 0.4, so you just follow this procedure. And this is valid for k is equal to 0, 1, 2, 3, etc. in integer form. And for less than 0, for k, the value is 0 for our time function. Okay, now let's bring it here and now evaluate this k, the function here, also at the specific values of k, in this case 0, 1, 2, 3, which will yield the following results. Now we just substitute here for k just 0. What happens? Now this Dirac delta function will be 1. This will be 0 because it's not valid anymore, or not active anymore. It is only active when this argument here in the parentheses will be 0. And this is 0.4 to the power 0 will be just 1. So what happens here? You get here minus 50 times 1, minus 20 times 0, that's actually shown here, and then plus 50 times 1. That is effectively 0 if you just calculate this. For k is 1, so we have then f1 capital letter T will be then minus 50 times the Dirac delta function 1t. This is 0 because it is only valid for 0 in the argument, and this is 0 because t minus t, so the capital letter T minus the capital letter T is 0, so it means we have here now a 1. So in total we have here actually minus 50 times 0, minus 20 times 1, plus 50 times 0.4 to the power 1, which is just 0.4, and that will also add up to 0. In this case we also have again a 0. Now for k is 2, we have now here f of 2 capital letter T will be then again the similar form, so you just use the k here. This will be again 0 because it is now 0, but now it is t, so the argument is not 0 anymore, so we will have 0 here, we have 0 here, and this will be then 50 times 0.4 squared. We'll get here now in this case 8. Now you can move on for k3 also in a similar form, so that will be then also again 0, 0, and now we have here 0.4 cubed, so to the power 3 we'll get here in total 50 times 0.064 will be then 32. Then we can write our inverse z transformation actually in this form, so this form will be then more compact using this form. And now we need to remember that the k is from 2, 3, 4, 5, so not valid for 0, 1 valid, because that it is valid, but it's not, it doesn't do anything because it's all 0. You can see that from the evaluation here. And for k is less than 2, it is 0. That's actually all the conclusion from here. Now we can now make the ideal sample time function using this summation. So we multiply our function using this delta function. As we did in the previous example, you just pick this and you now start your summation from k is equal to 2 up to infinity. And now we can develop our function, and we can present here the first 4 samples of the ideal sampled waveform. So k is 2, 3, 4, and 5. So just substitute here for k is 2, 3, 4, and 5. That means in here 2, and also here in 2. That means here 3, and also here in 3. So you just actually follow the summation. And now we need to work out this coefficient for each Dirac delta expression here. And that results in this one, so 8 times the direct delta function here, and now 3.2 here, and 1.28, and now 0.512. Okay, let's bring it here and move on out of the MATLAB command window. We see here the command for defining a symbolic scalar value, and then we express our function, which is here, and then we determine our inverse z-transform by this command iztrans, capital letter F, which is equal to the small letter f, and that is the result here, which is actually shown here. What you see is the following. You see here in the first term is 50 times 2 over 5 is 0.4 to the power n, which is the third term here. And this one, minus 20, Kronecker delta, is this delta function, and then it says in the first argument n minus 1 means it is shifted by 1 sample time, which is this function. And the final one is minus 50 Kronecker delta n, which is then the first term here. So we can say this is as we have also in the MATLAB, so this is verified. Alright, this was our example about the inverse z-transform of a function where we see the different variation of the result using this direct delta function and the delays. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video.